All right, welcome back. We're on the next lecture, and what we've been talking about is the arithmetic logic units, and we previously built let's take a look, we built a circuit using the 181 IC, which is the ALU, and that particular ALU had 32 different functions, 2 banks of 16. But I did not have that IC inside of my inventory. But what I do have in the inventory is the 382, and I have a 74F 382. All right, so we've built up this circuit here in Proteus, and we've talked about this. And what we're going to do now is we're going to take a look at the bench, and I've built this on the bench. And in a nutshell, what this does is we have 2 input operands that are 4-bit, A and B, and then these go into the arithmetic logic unit, A and B, and then we select the operation with these buttons here, and the default operation is clear. So if you don't input anything, it's always clearing as the 0, 0, 0 operation you can see in this table here. Low, 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 it's clearing. So any of these other bit patterns on S0, S1, S2 select these operations: B minus A minus B, A plus B, A XOR B, A or B, A and B, and preset. All right. Then what we did was we took a bunch of switches so that we could press buttons instead of set dip switches. And then we looked at what these values were, and then we created gate inputs to OR gates so that we figured out what S0, S1, and S2, what these inputs would need to be to facilitate each one of these operations with these buttons. All right, so each one of these are momentary buttons. All right, then let's see what else we have here. We have the displays. So we've got 7447s coming out of connected to the output of the ALU, so we can see the result. And then we've just picked off A and B and put those through 7447s to display drivers as well. Okay, so that is what we have here. And the only other thing is the carry-in, which the only time we care about that is if we're cascading something or if we're going to do a subtraction, you have to set the carry-in. And I think that's about it. So I've basically replicated this over on the development board, on the solderless breadboard. So let's go over and take a look at that and see what's going on there. All right, so let's go over to the bench, and what we're going to do is we're going to try some of these operations here and actually watch them output in real time. All right, so let's go over and take a look. Okay, so here we are on the bench, and this is the entire circuit here. All right, and so there's, I believe this one is A and this is B, or it's the other way around. We'll get to that in a second. And then here's the solution, or the output from the arithmetic logic unit. So, and here's the arithmetic logic unit. And then here's our 7432, our OR gates, which kind of create each one of these button presses. Here are those 3 selection lines that go into the 74F382. And then here's display driver, display driver, display driver. And then here's our carry in bit. So it's pretty straightforward. Now, the only thing, so I've just realized what I've left out here is the carry out and overflow bits. So the carry out, looking at the schematic, is on pin 14, and there it's inverted. So that means it's going to be active low. So why don't we, what do you think, use a red LED, little red LED? We'll use a red LED, and then let's get a 100 ohm resistor, and we'll put that in series. All right, so let's find pin 14 here. So the, and let's make sure these wires don't come out. We'll never figure out what's going on here. This took quite a long time to do this. And, you know, this is not the cleanest thing, but it's not the messiest thing either. It's not bad. There's, you know, I try to keep buses and all this. But again, you don't want to spend 20 hours building these things, right? You just want to get them to work, try things out. And then if it doesn't work, then you clean it up. All right, so pin 14 we're looking for on the 74F382. And the chip is a 20 pin, I believe. Let's count it right here. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's 20 pin, 10 on each side. And again, you know, constantly just do sanity checks. When you're counting pins, remember they go from pin 1, it increases, and then it wraps around this way counterclockwise always. So like these display drivers, I believe these are 16 pin, 1, 2, 3, 4, 5, 6, 7, 8, yeah, and the other 8 over there. You can look on the data sheet, of course, but just, that way it just kind of helps you. All right, so we want pin 14. So this is 1 through 10, 11, 12, 13, 14. So pin 14 is right there. Now, what I'm going to do, I think, is I'm going to bring a line. I'm trying to find a kind of a good place here to put this. So let's bring this way out. Let's bring this way out. So what we're going to do, pin 14, and again, this is, as you do this stuff, you got to kind of make these decisions as well. We could put it right here, but I kind of feel like I want it way over here. So what I'm going to do is I'm just going to take our resistor here, our current limiting resistor, and I'm going to put it right there. And then remember, this is active low, so I'm going to put the cathode towards the resistor, and then I'm going to connect this to high, like this. Okay, cathode is towards the resistor, all right? And then I'm going to run that to that output. And what do you think? Let's use maybe white, use a white wire. And you can see I tried to color code things a little bit so that as I'm wiring it up, and this is a good technique. So for example here, as I was making these different buses, I made this one green, this one blue, this one purple, and so on and so forth. So you can kind of see things, because otherwise you'll just get really, really confused. So let's go ahead and strip that wire a little bit. Okay, so right here, and it's going to go to 14. So 11, 12, 13, 14. Hope that's 14. 11, 12, 13, 14. Okay, that looks good. Okay, so there's our whole circuit now. We've at least got overflow here. All right, so now let's play around here. So the first thing is we've got our two operands here. And then we've got these dip switches right here, which select what the numbers are. So for example, and I've kind of colored them in green and colored them in blue here. So I'll put this up. So there's 7. And because we've got a 1, 1, 1 right there. So this is in binary. So this is the low bit, next high. So the 1 bit, the 2 bit, the 4 bit, the 8 bit, the 1 bit, the 2 bit, the 4 bit, the 8 bit. All right. So let's put that back. Let's see, what do we have there? Yeah, 3 and 5, and then we had 3 up here, so I could put that bit, and that would be 7. And then if I go and put a 15 on that, remember these displays blank out on 15. So we could put an 8, and a 4 is too much. That's 12. That's too much. That's 10. There we go. So 8 and 1 makes 9, right? 8 and 1 makes 9. Okay, so we've got two things here. We've got 9 and we've got 5, and let's try and figure out which thing is which here. So we got 9 and we got 5, and we're not sure which one is A and which one is B. So the little blue dip switch here has got these yellow wires, and for example, I've got one of those bits going to pin 1. So let's see if that's operand A or B. So pin 1 is A. All right, so this is definitely A right here, and then this is B. All right, so this is A, and then this is B. So A is this one, and then this is B right here. All right, that's the way it is. That's the way these buses are. So A is here, and B is here. All right, so just kind of remember that. Not going to matter too much. All right, so what I'm going to do right now is I'm going to just kind of turn this, because it'll make it easier so we don't have to rotate our heads 90 degrees. Now the buttons here represent all the operations that are in the design there. So they go from left to right, and the operations, I'm going to put them up on the screen here for a second for me, but they're just like in the table in the Proteus CAD file here, which is Crash Course ALU 74LS382_02, which of course will be in the course materials. So it's B minus A, that's this button right here, there's B minus A. The next one is A minus B, the next one is A plus B, the next one is A XOR B, and so on, all right? So let's try and do one of these and see if this works. Okay, so this first one is B minus A. All right, so B minus A, so that should be, this should be B, and this should be A. So B minus A should be 4, all right? So when I press this button, instantaneously, let's stop the camera from shaking. Instantaneously, we should see a 4 here on this output, and this is the output of the ALU. Ready? All right, so we got a 3. So what's going on? All right, so what's happening is we're doing a subtraction, so we have to put the carry in. We have to insert a carry in. So I'm going to put a carry in. I'm pushing down carry in. Now we do it. 9 minus 5 is 4. That is correct. All right, now let's do the other way around. What's 5 minus 9? Well, it's a negative number, and that negative number is going to end up being larger than what we can display. Because that bit pattern is not going to be displayable, so we get one of these symbols right here because this is working in 2's complement. So that's working. That's what we expect. So that's good. This next one is A plus B. We don't need to carry in. 9 plus 5, 9 plus 5 is 14. All right, so 9 plus 5 is 14, and we're going to get a funky symbol on here that represents 14. So if you look up the 7447 for 14, that's what you would see. Let's do something that'll actually fit on the display. So let's get rid of the 8's place here on B here. Very careful, I don't want to pull anything out. There we go. And let's put 5 and 5. That won't fit. 5 and 7. And let's get rid of that. There we go. How about 4 plus 9? Excuse me. 4 plus 5 will equal 9. 4 plus 5. So here's the plus operator. And sure enough, 4 and 5 equals 9. All right. Now, interestingly enough, 4 and 5, we get a 9, and we get this carry out right here. All right. So we get 4 plus 5 is 9. We get this carry out, and we shouldn't get a carry out. It might be thinking in BCD, and that's why we get that carry out. But anyway, we are getting this carry out here. All right, what's the next operation? Let's pick another operation. So the next one is A XOR B. A XOR B. All right, so 4 XOR 5. So convert 4 to binary, convert 5 to binary, and XOR them. That will be the result. So that is the 1, 2, 3, the fourth button. 1, 2, 3, the fourth button. So A XOR B is a 1. All right. Now, what I've got here is one of my new calculators here. And I think I've told you my daughter, she's 2, she likes to hide them. All right, so we're going to take this calculator, we're going to put it in we're going to put it in base n mode 4, all right? And then what we're going to do is we're going to put the first number in, we're going to say 4, all right? And then I want to XOR that. So in this particular calculator, we have to get the base n operations, which is here. We're going to select XOR, which is 3, if you can see that, XOR. All right, pretty cool. And we're going to XOR that with 5. And then when I press equals, you get the 1. And there it is. So that's correct. All right, so there's an XOR operation. We have anything else exciting? Let's see here. So A and B. So this operation right here, the one before the last, is A and B. All right, so 4 and 5. All right, so 4 and 5. So if you can do this in your head, 4 is just the 4-bit, 5 is the 4-bit and the 1-bit, right? So 4 and 5 will just be a 4. That's where we've got a 1 and a 1 in both positions. So it should be a 4, right? So there it is, and we get a 4. All right, and that's exactly what we expect. So anyway, it's working. So we got an ALU operating and doing calculations, and it can do math, and it can do logic operations. We have the basis of a computer. So let's go back to the blackboard here, the computer, and the PDF file, and I want to talk to you about kind of a little bit more about how you would, kind of make a computer, just some ideas about it that you could use this ALU with. So I'll meet you back at the computer. Okay, so we're back on the computer now, and we played with our little prototype, which took a lot of time hooking that thing up and getting it to work, kind of a pain. But as you can see, it mimicked this circuit, which we couldn't simulate because we do not have the 7.4 LS or F382. So anyway, you have the circuit. You can play with it and look at it. And the file is right up here, Crash Course EE ALU 74 LS 382_02. And that works here in Proteus. Now, what do I want to talk to you now? Okay, so we were talking about arithmetic logic units. We've gone through all this material. All right, and now what I'd like you to make sure you do is read this section in my book, 6353 on ALUs here. And what I'd like to talk to you about is, now this, hopefully, you know what, I think this is still, let me see here. Okay, let's see what happens if we click this. Yes, allow. Good. It opens up the browser. Okay, so this is kind of cool. So this is an example of like a homebrew CPU, and I believe this guy made this out of TTL chips. Yeah. A custom CPU made out of 74 series TTL chips, all right? So there are 200 chips in the Magic One. So this is a computer, made with the techniques that we're talking about, and all out of TTL chips. How cool is that? So this is very, very cool, and you could do worse things than read through all of this web page and stuff, all right? So I'd like you to do that just for fun. But anyway, what I'd like to bring your attention to for our coders out there is, and this is kind of C code, pseudocode. So if whatever language you program in, Python, C, C++, etc., you should be able to understand this. So what if we wanted to make a processor, right? And we're kind of thinking about doing something like that CPU I just showed you. All right, well, what we could do is we could think about if we just had some memory, like a RAM memory that we could access through, all right? And then let's say that we want to create an instruction set, and maybe each one of those instructions were like, one of these ALU operations and maybe a branch or a jump or something like that. And then to keep it real simple, maybe we say it's only 256 memory locations, so it's 8-bit. And then maybe to make it simpler, we have what's called a fixed instruction length, right? So the instruction is always the exact same size, so it's not 1 byte, 2 byte, 3 byte, 4 byte, whatever. It's always like 1 byte, 2 byte, 3 byte, 4 byte. So here's a little C code. So just kind of follow me here and see if you can kind of figure out what I'm doing. So let's assume that we create an unsigned array of bytes, so just bytes, and let's assume that we have we're going to put a program in here manually, and the program is going to consist of an opcode, two operands, operand 1, operand 2, and then a result. And you don't have to use either the operands or the result, but they're there. So the memory locations are there if you like them. So an opcode could not operate on the operands and not create a result. It could be like a nope, a no operation. Doesn't do anything except take up time. So these would be wasted bytes, but that's okay. All right, so this is how we would lay out our memory. All right, and this is another thing. If you're into emulators or programming things like that, like one of the things that I did when I was really young was I created a 6502 emulator, Z80 emulator, probably, I think, did I do an 8080 emulator? Maybe, but I would write processor emulators, and it's really fun because you basically just model the processor, and then it's pretty easy because it's just like, what's the opcode, what's the operand, and then just do the code, do the instruction inside of a little bit of code, and then you basically have a giant case statement that just runs through what the instruction is. Anyway, similar kind of thing here. So we've got our program here. Here it is. We got 256 different instructions here, whatever they happen to be. All right. And then create a variable unsigned char IP for an instruction pointer, right? And that's the thing that kind of runs through the memory. All right, then we come to our main here. All right, we reset the system. We set the instruction pointer to 0, then run forever while 1, right? And then, this is just pseudocode. All right, and then we say switch program IP. So what's that going to do? So program is this. It's just an array, and it's going to say switch program sub IP. That's going to access wherever the instruction pointer is pointing, which right now is 0, so it's going to point to this first opcode, right? Whatever that is. Then we go through here, and then we basically say, is it an add opcode? And maybe add is a 12, and maybe sub is a 39, and maybe and is a 42, right? They're encoded. So if it's an add, then we say, okay, program IP plus 3, that's where the result is stored, right, equals program IP plus 1 plus program IP plus 2. Those are the two operands. So that operand and that operand, and this would be the result. So it adds these two. So it basically adds the two operands and stores the result. All right. And then that's that. And then we would just implement all these instructions, then default break and switch, and then increment the instruction pointer. Because we're using fixed length instructions, it's always going to be IP plus equals 4, IP equals IP plus 4, just shorthand. All right. And then we just let it wrap around because it's an 8-bit value, so it's just going to wrap around. That's fine. Then we jump back up. That's it. So this basically is a really crude little instruction stream execution unit in C code that you could implement with this ALU, a counter, some memory, and a little bit more logic. We could actually implement that. and that code kind of in this hardware. And that's exactly what that CPU thing that I just showed you, this thing, this homebrew CPU, that's exactly what this kind of does on a more complex scale. And that's what a microprocessor or microcontroller does do. All right. So anyway, take a look at that, think about that, maybe write up a little bit of code in a JavaScript, Python, whatever your favorite code is, and try and implement that. And then of course just read through this right here, and kind of, I summarize how you would do that. So that is the end of this. We are done with all this chapter. The next chapter is going to get fairly advanced. We're going to stop in the next chapter basically, but we're going to, I believe we've got counters in the next chapter, so we're going to take a look at that so we can have that counter coverage. But the next chapter would be kind of a whole nother course, right, in advanced digital electronics. So we know enough now to do some damage. All right, so we're going to do a little bit more in the next chapter. We're going to look over that, chapter 7. So if you want to read ahead, go ahead. And then after we talk about counters, then we're going to start building circuits with Circuit Maker, finally. So we're going to build a number of cool little circuits. I don't know, we'll just kind of do it as we go, and just get the hang of doing Circuit Maker, make some basic circuits, make their Gerber files, and then figure out how would you send these out for manufacturing and all that. So we're to the last part of the course, and we finally are to the funnest part, because now we can actually build things, which is going to be really cool with all that we know. So now we are, basically, sort of electrical engineers, right? Embedded engineers, right? And we know enough to kind of do what we need to do. All right. So see you in the next lecture. Bye.